Today we're going to talk about a mathematical master key. It's a technique that lets us unlock equations describing our universe, equations that, for all intents and purposes, seem completely unsolvable. So let's dive right in.
So let's start with a little puzzle. Think about sound waves, vibrating through the air. Then think about heat spreading across a metal plate. And then the totally weird, probabilistic world of a quantum atom. On the surface, they have nothing to do with each other. But what's the hidden thread connecting them all?
Well, here's the wild part. The math that describes all of these phenomena, it relies on equations that our standard toolkit just can't crack. Yeah, the methods we all learned in school, they hit a wall. And that's the real challenge we're tackling.
To really appreciate how amazing this master key is, we first have to get a good look at the lock. So let's explore the limits of our everyday mathematical tools.
Think back to your math classes, right? You spent all that time with polynomials, sine and cosine waves, exponential growth, logarithms. Mathematicians call these the elementary functions. They're the powerful, reliable workhorses of math, and honestly, they solve a ton of problems. But not all of them.
And this is a huge deal. As the source material points out, for a massive class of really important equations, these second-order linear ones, our trusty elementary functions often just fail. We're talking about the very equations that describe things like acceleration and vibrations, stuff that's fundamental to physics and engineering. It means the answers we need are hiding somewhere just beyond our normal reach.
So, if the solutions aren't these familiar elementary functions, then what in the world are they? Well, there's something new, something a bit more exotic. These are what mathematicians call special functions. They are the very answers we're looking for, hiding in plain sight.
So how do we actually find these elusive special functions? This is where the hero of our story comes in, a technique so powerful it can literally build the solutions right from scratch. Let's see how this magic key works.
Okay, meet the power series. You know how a polynomial has a finite number of terms? A power series is kind of like an infinite polynomial. It just keeps going and going. And here's the brilliant idea. With enough terms, this infinite series can bend and curve and twist to perfectly match any well-behaved function, including the special ones we're hunting for.
The method itself is this incredibly clever four-step recipe. First, you just make a really bold assumption. You say, okay, what if the solution I'm looking for is a power series? Then you take that series and you plug it into your unsolvable equation. Now, this creates a giant algebraic puzzle, but it's one you can solve. The goal is to find a pattern, a rule that tells you how to get each new coefficient from the ones before it. And once you have that rule, you can build the exact solution piece by piece.
This is so much more than a neat trick. It is a total game changer. It gives us a systematic way to construct answers for equations that used to be considered dead ends. We're essentially building the key from the shape of the lock itself.
But, like any powerful tool, you have to know how and where to use it. The method has this crucial decision point built right into it, and it all comes down to the nature of the equation itself.
The secret is hiding in the equation's coefficients. We'll just call them p of x and q of x. How these two functions behave at a specific spot on the graph tells us everything we need to know. They tell us if our key is going to fit smoothly or if we need to jiggle it a little.
This leads to two different situations. If, at the point we're looking at, both p of x and q of x are well-behaved, we call it an ordinary point. The power series method works perfectly, just like we described. But if one of them starts to misbehave, like say it tries to divide by 0, we've got ourselves a singular point. The method still works, which is amazing, but it requires a clever little tweak.
So, analyzing the equation tells us if we're dealing with an ordinary or a singular point. And that, in turn, tells us which version of the power series method to pull out of our toolbox. It's the diagnostic step that makes the whole thing work so beautifully.
All right, that's enough theory. Let's actually see this master key in action. We are going to unlock our first treasure, a really famous family of special functions. This is Legendre's equation. I know, it looks a little intimidating, but it's a huge deal in physics, showing up in electromagnetism and quantum mechanics. And the crucial thing for us is that its solutions are not elementary functions. It's the perfect locked door to test our new key on. So we'll look at the point where x equals 0. Turns out it's a nice, well-behaved ordinary point. So we get to use the standard power series method. We substitute our infinite polynomial, we turn the algebraic crank, and after a whole lot of careful work, a beautiful, clear pattern emerges, a rule for finding all the coefficients. But here, okay, this is where the real magic happens. See that little constant p in the equation?
Well, it turns out that if you choose p to be a whole number, like 0, 1, 2, or 3, something absolutely incredible occurs. One of the infinite series solutions just terminates. It stops. It becomes a regular, finite polynomial.
And these are the results. For each whole number you pick for p, you get a unique polynomial. This whole family of solutions is what we call the Legendre polynomials. These weren't tools we brought to the problem, they were the treasure, hidden inside the equation from the very beginning, just waiting for the right key to reveal them.
So, was that just a lucky fluke? Or is this key a true master key? Well, let's see what other treasures it can unlock. Next up is another celebrity in the world of mathematical physics, Bessel's equation. This one describes everything from the way a drumhead vibrates to how radio waves travel. And, just like Legendre's equation, its solutions are not elementary.
So we apply the power series method, the modified version this time, since x equals 0 is a singular point here. And boom, out pop these beautiful wavy Bessel functions. These are absolutely indispensable tools in signal processing, acoustics, fluid dynamics, all of them, revealed by the exact same method. So let's just recap the power of this idea for a second. We started with equations that we just couldn't solve using our standard toolkit. This one method not only solves them, but in the process, it actually reveals entirely new mathematical objects, these special functions, which then become essential tools for describing the physical world around us.
And that leaves us with one final, mind-bending question. The power series method showed us that the solutions to some of the most important equations were just hiding in plain sight all along. It really makes you wonder, what other secrets are still lying dormant in the math of our universe, just waiting for the next master key to be found?